Welcome back to our 42-day journey into mastering the standard template library in C++. We have already explored vectors in depth, and now we are going to meet their flexible cousin, the DQ. Today is day 8, and our focus is on understanding what a DQ is, how it functions under the hood, why and when we would choose it over vectors or lists, and of course, how to use it effectively in real code. By the end of this session, you will not only understand a DQ, but also be ready to solve real problems with me. A DQ or the double-ended queue is a highly versatile container that allows us to insert and delete elements efficiently at both the front and back. It's a sequence container just like a vector or a list, but with some key differences. Think of it as a hybrid. It gives us fast insertions at both ends like a list and random access like a vector. So if we ever need the benefits of both, the DQ is a perfect choice. We will explore exactly how and why next. Now let's peek under the hood. Unlike vectors, which rely on a contiguous block of memory, DQs use a segmented memory model. That means they allocate multiple smaller blocks dynamically rather than trying to grow one large contiguous chunk. This difference allows us to insert elements at the front without shifting the entire container, unlike with vectors. This structure makes DQs especially useful in scenarios where we constantly modify both ends of the sequence. Working with a DQ in C++ is straightforward. The interface is quite similar to that of a vector, with a few key additions. We can insert at the back using pushback and at the front using pushfront. Likewise, we can remove elements using popback or popfront. For accessing elements, we have front, back, add index, and the subscript operator. The queues also support clear, empty, and size, which make managing them quite convenient. Here's a basic example to show how we can use a DQ. First, we push a 10 to the back and a 20 to the front. So now our DQ contains 20 followed by 10. When we print the front and back, we get 20 and 10. Then we remove the front and back and we are left with an empty DQ. This illustrates how cleanly and symmetrically a DQ works from both ends. Now let's look at some practical use cases. One of the most common is solving sliding window path problems, where we need to insert and remove elements from both ends of a sequence. DQs also help in implementing undo and redo systems where actions are pushed and popped depending on user behavior. They are also great in palindrome checking, where we compare elements from both ends, and even in task scheduling, where we can dynamically add or remove tasks based on priority. In short, DQs show up in many real-world applications. So when should we use a DQ? The general rule is if we need fast insertions and deletions at both ends, and we also want random access to elements, then the DQ is the ideal container. If our problem involves a lot of insertions or deletions in the middle, a list might be better suited. DQs really shine when we work with problems where the ends are active but the middle stays mostly untouched. This table gives us a clear comparison of vectors, lists, and DQ. Vectors provide fast random access and are efficient for back insertions, but struggle with insertions at the front. Lists excel at front, back, and even middle insertions, but don't support random access. DQs sit right in the middle. They offer random access and are efficient at both ends, but not optimal for middle insertions. Also, unlike vectors, DQs don't store elements in contiguous memory blocks. Let's try a hands-on exercise. We will insert integers into a DQ using both push front and push back. After every insertion, we will print the front and back elements, and for a bonus challenge, let's remove all numbers greater than 100 from both ends of the DQ using a loop. This exercise helps reinforce our understanding of insertion, access, and conditional removal. To sum it up, DQs are highly flexible containers, giving us the best of both vectors and lists. They are efficient for front and back operations and allow us to access elements by index. They are ideal for real-world problems like undo systems, task scheduling, and sliding window algorithms. For homework, let's explore using PQ with iterators and try out STL algorithms like reverse, remove if, or rotate. Also take a moment to explore the official C++ documentation to deepen your understanding. Up next, we will explore the list container and how it differs in structure and usage. See you in day 9. Welcome to day 9 of our STL journey. Today we are exploring a very important container, std::list, which is STL's implementation of a doubly linked list. By the end of this session, you will be able to confidently insert, delete, and traverse element in a list, compare its performance with vectors, and most importantly, know when to use it in real-world development scenarios. So what exactly is std::list? It's a doubly linked list that's part of a standard template library. Unlike vectors or arrays, it does not store elements in contiguous memory. This unique structure means that inserting or deleting elements anywhere in the list, even in the middle, is fast and efficient. But there's a trade-off. You can't use the bracket operator to access elements like you would do in a vector. There's no random access. You have to use iterators to move through it. Let's take a peek inside. A doubly linked list is made up of nodes. Each node contains three parts: the data itself, a pointer to the previous node, and a pointer to the next node. These nodes are chained together both forwards and backwards. Because of this setup, we can insert or delete elements at any known position in constant time. No shifting required, unlike vectors. Declaring and initializing a std::list is quite straightforward. You can start with an empty list like std::list int list1 or initialize it directly with values. Lists can also hold other types like std::string, float, or even custom objects. The syntax remains consistent with other STL containers, which makes it beginner friendly. Let's go over some basic operations you will often use with lists. Pushback adds an element to the end. Push front adds to the front. Insert allows inserting at any position using an iterator. And popback or pop front removes element from the respective ends. It's important to note that insert and erase work with iterators, not indices. That's a major distinction from vectors. To go through a list, we primarily use iterators. We start from begin and move till end, dereferencing the iterator to access each element. Alternatively, we can use a range-based for loop, which is more concise and readable when we just need to access elements one by one. Both approaches are valid. Use whichever suits the context of your code. Beyond the basics, std::list comes with several powerful built-in functions. Sort lets us sort the elements. Unique removes consecutive duplicates. Reverse reverses the list in place. And remove deletes all occurrences of a specific value. Another standout feature is merge, which merges two sorted lists into one. It's extremely useful in merge sort like algorithms, or any merging workflows. Let's compare list and vector side by side. Random access. Vector wins because it requires big of one access time with indexing. List has none. Insertion and deletion in the middle. List wins constant time if you have the iterator. Cache performance. Vectors perform better thanks to contiguous memory. Memory overhead. Lists consume more memory due to the extra pointers in each node. So lists are great for frequent modifications, but vectors are better when you care about access speed and memory efficiency. So when should you actually use list? Use it when you have frequent insertions or deletions in the middle of your sequence. Use it when the order of elements matters and you don't need random access. Also, if vector reallocation is causing performance issues, a list might be a better alternative. but avoid it if you need fast indexed access or if you are working in a memory sensitive environment, because that extra pointer data does add up. Here are a few common mistakes developers make with list. Trying to access elements using list I. This will not work. Applying algorithms like sort from algorithm. These expect random access, which lists don't support. Forgetting to use iterators with functions like insert and erase leads to compilation errors, or runtime bugs. Understanding these limitations early on will save you from a lot of frustration later. Let's test your understanding with a few mini challenges. Write a function that reverses a list manually. Merge two pre-sorted lists using merge. Sort a list and remove duplicates using sort and unique. Create a list of strings and remove specific values. These will give you good hands-on practice and help solidify your understanding of list operations. To summarize, list is a doubly linked list offering efficient insertions and deletions. It's perfect for situations where data changes frequently in the middle of the sequence, but you sacrifice random access and incur extra memory usage because of the internal pointers. Choosing the right container depends on the task, and now you know exactly where a list fits in. Great job finishing day 9. Let's keep the momentum going. Hello and welcome back to our journey through the standard template library in C++. Today is day 10 and we are going to take a deep dive into one of the most fundamental and widely used data structures, the stack. We will explore how it works using the LIFO principle, learn about the std::: stack container adapter in STL, understand the operations it supports, and see how it leverages other containers like vectors and TQs under the hood. By the end of today's session, you will not only be comfortable using stacks in code, but also understand where and why to use them effectively. Here's what on our roadmap for today. First, we will understand what a stack is conceptually, how it behaves, and where the LIFO principle comes in. Then we will explore std::: stack in STL, its syntax, methods, and the containers it builds upon. We will walk through code examples, discuss time complexities, and analyze practical use cases. Toward the end, we will look at how to build a simple stack manually using vectors and TQs, cover common mistakes developers make, and finally wrap it up with hands-on practice problems and your homework for the day. Let's begin. So what exactly is a stack? A stack is a linear data structure that follows the last in, first out, or LIFO order of operations. Think of it like a stack of plates in your kitchen cabinet. The last plate you put on is the first one you take out. You can't remove a plate from the bottom without removing the ones above it. Similarly, in a stack, the last element pushed in is the first one that comes out. This simplicity makes stacks powerful for managing data in a controlled, predictable way. Let's talk more about LIFO, or last in first out. Imagine you are pushing integers onto a stack in the following order: 10, 20, and 30. The last element you inserted is 30. It's now on top. When you perform a pop, 30 is removed and the new top becomes 20. So the last value pushed in is always the first to come out. This behavior is extremely useful in programming, especially in scenarios like function calls, undo operations, and parsing expressions where you need to reverse or backtrack through elements. C++ makes it easy to use stacks through its STL, the standard template library, with the std::: stack class. It's defined in the stack header and is what we call a container adapter. This means that it does not store elements on its own. Instead, it adapts existing containers like TQ, vector, or list. By default, it uses TQ. The stack interface gives us just what we need for a LIFO structure: push, pop, top, empty, and size. Nothing more, nothing less. It's a focused tool for focused use cases. Let's look at the core functions STD: stack provides. First, push adds an element to the top of the stack. Pop removes the element at the top, and note it does not return it. So you will want to call top beforehand if you need to access it. Top lets you pick at the element on top without removing it. Empty checks if the stack has no elements, and size returns how many elements are currently in the stack. These operations give us all the control we need to work within the LIFO paradigm efficiently. Here's a short code example that demonstrates stack operations. We create a stack of integers, then push two values onto it, 10 and 20. When we call top, it returns 20, the most recently added element. Then we pop the stack removing 20, and now top returns 10. This simple sequence clearly shows how the LIFO mechanism plays out in real time. You will be using this behavior frequently in algorithms and logic-heavy applications. One interesting thing about STD: stack is that it does not function alone. It wraps around another container. This is what makes it a container adapter. By default, it uses a DQ because DQs offer efficient insertions and deletions from both ends. However, you can also use a vector or a list if your use case demands it. For example, if you don't need frequent pops but want tight memory allocation, vector may be ideal. When performance tuning, the choice of underlying container can make a significant difference. Time to talk about performance. All core stack operations push, pop, top, empty, and size are constant time or peak of 1. This means that no matter how many elements are in the stack, each of these operations will complete in the same time. This predictability and speed are a big reason why stacks are a go-to structure in both real-time applications and algorithm design. Stacks are everywhere in the programming world. Think about the undo feature in a text editor. Every change you make is pushed onto a stack. When you hit undo, the topmost change is popped. They are also used for parsing expressions in compilers, balancing symbols like brackets and parentheses before performing depth-first search in graphs and managing recursive calls. Understanding stacks is like having a Swiss Army knife in your algorithm toolkit. While STL gives us a ready-made stack, understanding how to build one manually depends our grasp. Here we implement the stack using a vector. The push operation becomes pushback, pop becomes popback, and top becomes back. This version behaves just like an STL stack but gives us more control and transparency, perfect for debugging, customizing, or learning purposes. Now let's do the same thing but with a DQ. The logic is almost identical, but under the hood a DQ offers more flexibility in insertion and deletion at both ends. This version might be more performant in some cases where bidirectional access is useful. Again, pushback, popback, and back mirror the standard stack operations. Knowing how to switch containers like this will help you tailor your solution to the problem at hand. Even a simple data structure like a stack can trip you up. A common mistake is trying to access the top element or pop an element when the stack is empty. This leads to undefined behavior or crashes. Always check with memory with empty first. Also remember that stack does not support iterators or random access. You can't loop through it directly or access the third element. It's strictly top only access. Keep these limitations in mind when designing your logic. Time to get your hands dirty. Here are some problems to reinforce your understanding. Try checking if parentheses are balanced in the string, a classic stack problem. Reverse a string using a stack, perfect for mastering push and pop. Convert an infix expression to postfix. This will challenge your logic and operator handling. And try simulating an undo system with two stacks. This one's fun and practical. These exercises are designed to stretch your understanding and improve your problem solving skills. Let's summarize what we learned today. A stack is a linear data structure based on LIFO, last in first out. The stack class in STL provides a clean interface for stack operations and relies on other containers like DQ or vector to do the heavy lifting. We explored its methods, looked at manual implementations, discussed time complexities, and saw how stacks are used in the real world, from text editors to graph traversal. Stacks may be simple, but they are profoundly useful. Here's your assignment for today. First, solve the valid parenthesis problem on LeetCode. It's a textbook example of stack application. Then implement your own stack class using both vector and DQ to really understand the internals. Finally, take some time to read about how the call stack works during recursion. This is a foundational computer science concept that connects beautifully with what we learned today. You are now equipped with the knowledge. Let's put it into action. Welcome to day 11 of our comprehensive STL course. In today's session, we will dive into one of the most fundamental yet powerful data structures, the queue. We will explore how the queue adheres to the first in first out principle, commonly known as FIFO, and how the C++ standard template library provides us with a robust and efficient queue implementation. By the end of this lesson, you will be confident in using queues to solve real-world and competitive programming problems. So let's get started. Let's begin by understanding what a queue actually is. A queue is a linear data structure that maintains the order of elements based on the first in first out model. This means that the first element inserted into the queue is the first one to be removed, just like waiting in line at a store or a service counter. You can only add new elements at the back and only remove them from the front. In real-world applications, queues are everywhere, from managing customers waiting in the line to buffering tasks in print queues to scheduling processes in operating systems. The queue enforces fairness by ensuring that requests are served in the order they arrive. To visualize the concept better, think about a real-life queue, like a line at a ticket counter. People join from the back and the counter serves the person at the front. There's no skipping and no random access, just a clean and fair process. This is exactly how a queue works in computer science. Understanding this analogy helps us relate abstract concepts to everyday experiences, which makes it easier to remember and implement them correctly. In C++, the standard template library gives us a ready-to-use queue container. To use it, we simply include the queue header. The std::: queue is implemented as a container adapter, meaning it wraps around another container, typically DQ or list, and restricts access to only the operations allowed in a queue. This abstraction allows us to focus on the queue's behavior rather than worrying about how it's implemented internally. And since it's built on top of efficient containers, performance is generally very good for typical use cases. Let's now look at the key functions provided by std::: queue. Push is used to insert an element at the back of the queue. Pop removes the front element, the one that was inserted first. Front returns a reference to the element at the front. Path gives you access to the most recently added element. Empty checks if the queue is currently empty, and size returns number of elements in the queue. These 6 functions are all you need to perform typical queue operations: insert, remove, check status, and access the ends. Now you might be wondering what data structure actually holds the elements inside a queue. Well, by default, queue uses DQ, which stands for doubly ended queue, as its underlying container. A DQ supports fast insertion and removal from both ends, making it ideal for implementing a queue. However, STL also allows you to change the underlying container. For example, you could use a list instead, if that fits your needs better. The only requirement is that the container must support pushback, pop front, and access to both front and back elements. This gives you some flexibility depending on performance or memory considerations. Let's take a look at a simple code snippet to see how a queue works in practice. We declare a queue of strings and push two names, Alice and Bob. When we call Bob, Alice is removed from the front, so now we access front, we get Bob, who is next in line. This short example clearly demonstrates the FIFO behavior. The first person in is the first one served. Such usage is common in simulations, task dispatchers, and real-time systems. While the queue is a very useful structure, it's important to understand its limitations. First, you cannot randomly access elements inside a queue. Unlike vectors or arrays, there's no bracket operator or .add method. You can't jump to the third element, you only interact with the front and back. Second, there's no support for iterators. This means you can't loop through the elements of a queue using range-based for loops or iterators. These restrictions are by design. A queue is meant to be a strict FIFO structure, and allowing access to the middle would break that model. So where are queues used in practice? One major use is in breadth-first search, a graph traversal algorithm that explores nodes level by level. BFS relies on queues to ensure nodes are visited in the correct order. Job scheduling systems use queues to process tasks in order of arrival, ensuring fairness and predictability. Customer service applications use queues to store and serve support tickets. Any system where order and fairness matter is a potential use case for a queue. It's time to get your hands dirty with a small coding challenge. Create a queue-based container service system. Ask the user to enter customer names one by one. When they type exit, stop taking input. Then serve the customers in the same order they arrived by using pop and show the name of the customer currently being served using front. This is a great way to reinforce how queues manage and serve data in a fair and ordered manner. Let's take a moment to review with a quick quiz. First, what is the default container used by queue? Second, can you iterate through a queue like you can with a vector? And finally, what are the time complexities of push and pop in a queue? Pause here, reflect on these questions, and if needed, revisit the slides. These checks help ensure you are grasping the key takeaways. To wrap up, queues are essential structures for ordered processing. STL's std: queue offers a clean and efficient interface for FIFO operations. It uses a DQ by default but supports other containers like list. You have learned the core functions, seen a live example, and explored real-world applications from graphs to customer queues. While queues are limited in terms of access and iteration, they shine wherever order and fairness are required. In the next session, we will explore priority queues where elements are served not just by order of arrival but based on priority. Until then, keep practicing and happy coding. Welcome back to our STL journey. This is day 12 and today's focus is on one of the most powerful data structures for solving problems where priority matters, the priority queue. Whether you are dealing with scheduling systems, graph algorithms, or anytime elements need to be processed by importance rather than arrival time, the priority queue is your tool of choice. We will understand how it works, how to use it for both max and min heaps, and how to tailor it with custom comparators for advanced use cases. A priority queue is just like a regular queue, with one key difference. Instead of serving elements in the order they arrive, it always serves the element with the highest priority first. That means the element with the largest value or smallest, depending on how you define priority, comes out first. Think of it like an emergency room. Patients are treated by arrival time, but by how critical their condition is. Behind the scenes, STL implements this using a binary heap, which is a complete binary tree structure optimized for such optimizations. In C++, the priority queue is provided as a container adapter inside the queue header. This means it wraps around another container, typically a vector, and modifies its behavior to prioritize certain elements. By default, it works as a max heap, so the largest element is always accessible at the top. This is done using the less t comparator, which gives precedence to higher values. All you need to do is declare a priority queue int and start pushing elements into it. The heap property is maintained automatically. Let's look at a basic example. We declare a priority queue int and push three values 10, 20 and 5. The queue automatically arranges them so that the largest element, in this case 20, is at the top. When we call top, we get 20. After popping it, 10 becomes the new top. The priority queue ensures that each time you pop an element, the next largest one is promoted to the top. This is the default max heap behavior, simple yet powerful. Now, what if we want the smallest element to come out first? This is where min heaps come into play. By default, priority queue does not support min heap behavior, but we can achieve it easily using a comparator. We define the queue with three template parameters: the type of the elements, underlying container, and the comparator. By passing greater int as the comparator, we flip the default behavior. Now the smallest element always rises on the top. This is particularly useful in algorithms like Dijkstra's shortest path, where we want to always process the nearest node next. Let's quickly go over the performance. Accessing the top element, the highest or lowest priority, is a constant time operation. That's because the top of the heap is always at the root. Pushing a new element or popping the top element both take log n time, where n is the number of elements in the queue. That this logarithmic time comes from the need to maintain the heap structure through up heaping or down heaping. These efficient operations make priority queue a highly effective tool for real-time and large-scale computations. Sometimes you will work with more complex data like structs or pairs, where the default comparison isn't enough. That's where custom comparators shine. A comparator is simply a callable object, typically a struct with an overloaded operator. This function takes two elements and returns true or false based on your custom priority rules. You might want to prioritize by deadlines, sports, weights, anything. By injecting your logic into a comparator, you gain full control over how elements are ordered in the queue. Here's a real-world scenario. Let's say we are working with a list of tasks, each represented as a pair of integers, task ID and priority. We want our priority queues to order tasks based on their second value, the priority. Using a custom comparator, we define the ordering logic and STL takes care of the rest. Now when you insert task into the queue, they will automatically be sorted based on how urgent they are. This is a foundational skill for coding interviews and advanced problem solving. Before we move on, let's talk about some common mistakes. First, forgetting to use greater for a min heap. This will silently give you the wrong behavior. Second, calling pop before top. Remember, pop removes the top element, but it does not return it. So if you forget to call top first, you lose that data. Third, confusing priority queue with queue or stack. A queue works in FIFO order, a stack in LIFO, but a priority queue is based entirely on value-based ordering. Always keep that difference in mind. To solidify your understanding, try applying priority queue in practical problems. Start with the classic, find the top k largest or smallest elements in an array, a great way to get comfortable with heap usage. Then move on to something more dynamic, like finding the median in a stream of numbers, which requires two heaps. Finally, attempt merging k-sorted arrays, a common use case where a min heap shines. These problems will not only build your STL skills but also prepare you for real coding interviews. The priority queue isn't just a classroom concept, it's used everywhere. In operating systems, it manages process scheduling so that high priority tasks run first. In network routing, it ensures critical data packets are transmitted with priority. In graph algorithms like Dijkstra's or Twins, it ensures the most optimal node is always processed next. Even in AI simulations or event-driven systems, it handles a sequence of events based on time or urgency. Mastering these tools equip you to build systems that are fast, responsive, and smart. To wrap up today's session, here's your homework. First, solve two lead code problems that require priority queue. This will give you a chance to practice both max and min heaps in real problems. Next, simulate an emergency room queue where patients are treated based on severity. Use custom comparators here. And for those of you seeking an extra challenge, design a toggle-able priority queue, one that can switch between min heap and max heap modes at runtime. These exercises will push your understanding and make sure you truly own this concept. Welcome to day 13 of our STL course. Today is entirely focused on practicing what we have learned. We will reinforce the fundamentals of stacks and queues through hands-on coding problems. Our goal is to sharpen your ability to think algorithmically using STL. We have curated 4 stack problems and 4 queue problems, each covering different patterns and levels of difficulty. We will also discuss debugging methods, analyze time complexities, and walk through efficient solutions. Let's dive into this problem-solving adventure. Before we dive into coding, let's quickly refresh our understanding of stacks and queues. Stacks follow a last-in, first-out pattern, ideal for problems where the most recent element needs to be accessed first. Think function calls or undo operations. Operations like push, pop, and top are key. Queues, on the other hand, are first in, first out, used when order matters, like scheduling or buffering. Both are backed by efficient containers like BQ and offer constant time complexity for most operations, making them perfect for real-time tasks. This is a classic problem often asked in interviews. The challenge is to validate whether a string of brackets is correctly nested and closed. We use a stack to store opening brackets as we encounter them. When a closing bracket appears, we check if it matches the top of the stack. If at any point it does not, or if the stack isn't empty at the end, the string is invalid. This is a great demonstration of stack behavior in parsing problems. In this problem, you are asked to find the next greater number for each element in an array. A naive approach is big of and square, but using a monotonic stack, we can reduce it to linear time. The idea is to keep a stack of elements in decreasing order. As we move when conditions are met, this efficient stack problem is common in many optimization scenarios. This one's a twist on the regular stack. Alongside standard stack operations, we need to retrieve the minimum element in constant time. The trick: use a second stack to track minimum values. Every time you push, compare it with the current min and update accordingly. When you pop, remove from both stacks. This dual stack setup is a great way to enhance basic data structures with additional features. Here we evaluate expressions written in reverse Polish notation, where operations follow their operands. This means no parentheses and no precedence confusion. We use a stack to store numbers. When an operator is encountered, we pop the last two numbers, apply the operation, and push the result back. It's a great example of how stacks are used in interpreters, compilers, and calculators. This problem simulates a live stream of characters where you need to identify the first non-repeating character at every point. We use a queue to maintain the order of characters and a hash map to track frequencies. As we iterate, we remove characters from the front of the queue if their count exceeds 1. This problem teaches us how queues are ideal for maintaining order under dynamic conditions. In this design challenge, we implement a circular queue that wraps around once it reaches the end. We manage it using a fixed size vector and pointers for the front and rear. This structure is used in buffering data, task scheduling, and memory-limited environments. It's a practical application of queues in systems programming and shows the real-world importance of efficient container design. This is a high frequency interview question. You are given an array and a window size, and you need to return the maximum element in each sliding window. A brute force approach works but isn't optimal. Instead, we use a DQ to store indices in a way that ensures the front always contains the current maximum. As the window slides, we remove out of window elements and maintain decreasing order. This highlights how queues can drastically improve performance in sliding window scenarios. This grid-based problem simulates how rot spreads among oranges over time. Each minute, rotten oranges infect adjacent fresh ones. We use a queue to implement a breadth-first search, treating each minute as a level in the BFS tree. By counting the levels, we calculate the total time to rot all fresh oranges. If we can't reach some fresh oranges, we return -1. This problem is a strong example of BFS in metric-based traversal. When debugging stack or queue problems, visualization is key. Use print statements to track changes in your container. Watch for off by one errors, especially when dealing with indices and loops. Also, don't ignore space complexities. Optimize memory where possible. Prefer DQ over list in most STL contexts due to better performance. And always consider edge cases. They often reveal hidden bugs and edge logic. Great job for today. To reinforce what we have learned, try solving at least 6 of the 8 problems. Push your solutions to GitHub. It not only tracks your progress but also builds your portfolio. Revisit STL documentation for stack and queue if you need a refresher. And for those who want an extra challenge, try implementing a stack using a list container from scratch. Keep coding and see you in the next session. Welcome to day 14 and congratulations on completing week 2 of your STL journey. You have now covered 5 essential containers: DQ, list, stack, queue, and priority queue. Each of these plays a crucial role in real-world problem solving. Today is about revisiting what we have learned, reinforcing the key concepts, and testing your knowledge through an interactive quiz. The goal here is not just to memorize, but to deepen your understanding and build confidence as we move into more complex STL containers in week 3. Let's dive in. Let's start with the DQ, short for doubly ended queue. What makes it unique is that it allows you to insert and remove elements from both the front and the back. This gives it a performance advantage in many scenarios where both ends of a sequence need to be accessed efficiently. Under the hood, a DQ uses a segmented dynamic array. This means it does not reallocate memory as frequently as a vector when resizing, especially at the front. You will often see DQ used in problems like the sliding window maximum, where you need quick front and back operations. Think of it as a flexible and efficient alternative to vectors when two-end access is required. Next up, we have the STL list, specifically a doubly linked list. Unlike vectors and DQs that use contiguous memory, a list is made of nodes that are spread out in memory and connected through pointers. This structure allows for extremely efficient insertions and deletions, especially in the middle of the list, something that vectors and DQs can't do efficiently. However, there's a trade-off. Since the elements aren't stored in a contiguous block, you can't access them randomly with square brackets. You have to traverse the list using iterators. Use lists when your operations involve frequent modifications, especially in the middle of the sequence, and not when you need fast access by index. Now let's review the stack, a classic last in first out or LIFO structure. This container is extremely useful in problems that require backtracking, recursion simulation, or tracking nested structures like brackets or function calls. The key functions are push to insert, pop to remove, and top to view the last inserted elements. Internally, a stack can be implemented using a vector, DQ, or even a list, but it restricts access to only one end, the top, so you can't iterate or access other elements directly. If you need to examine elements, you will have to pop them off one by one. Think of it as a controlled access container that mirrors real-world stack behavior. Let's cover two more containers, queue and priority queue. A queue is a first in first out or FIFO structure, just like a line at a store. You insert at the back with push and remove from the front with pop. It's ideal for task scheduling, process management, and breadth-first search. On the other hand, a priority queue is a container that always gives access to the element with the highest priority. By default, it behaves like a max heap, meaning the largest element is always at the top. But with a custom comparator, you can turn it into a mean heap, useful for Dijkstra's algorithm or when you need the smallest element. Internally, a priority queue is backed by a vector and uses heap algorithms to maintain order. Now let's look at some common mistakes students often make when working with these containers. First, never access the top of a stack or the front of a queue without first checking if the container is empty. Doing so could lead to crashes or undefined behavior. Next, remember that list does not support square bracket access. It's not an array. Another common misconception is thinking that a priority queue is fully sorted. It's not. Only the top element is guaranteed to be the highest priority. The rest are in heap order. Finally, it's easy to confuse front and back when working with DQs, especially when popping elements from both ends. Watch out for this. They can trip you up during coding or interviews. Alright, it's time to challenge yourself with a quiz. This one has 10 questions that mix theory and practice. There are 5 multiple choice questions to test your conceptual clarity, 3 output based questions where you will predict what a piece of code will produce, and 2 debug the code problems that require spotting and fixing logical or syntax issues. Take your time, pause the video if needed, and really try to solve them before checking the answers. This is your checkpoint to ensure you are truly grasping what we have covered. Let's go through the quiz together. For each question, I will give you the correct answer and explain the reason behind it. This isn't just about being right or wrong, it's about learning why. We will also highlight common mistakes and clear up any misconceptions. These explanations will strengthen your conceptual foundation and prepare you better for real world coding, interviews, and contests. Looking ahead to week 3, we are entering the world of associative containers. This includes sets and maps, both in ordered and unordered forms. You will learn how to store key value pairs before lookups in constant time. Even customize how elements are compared using custom comparators. We will also take a deep dive into iterators, a critical topic that empowers you to traverse containers effectively. Week 3 also includes a mid-course quiz to evaluate your learning progress. It's going to be an exciting and intellectually rewarding week. You have done a phenomenal job completing week 2. These containers you have studied from the foundation of efficient problem solving in C++. Remember, mastery isn't about rushing. It comes from repeating, reflection, and application. So keep practicing, code daily, review what you have learned, and tackle real problems from platforms like LeetCode or Codeforces. And most importantly, stay curious and don't be afraid to ask questions. You are building a strong code toolkit that will serve you throughout your software development journey. Let's keep going and make week 3 even more awesome.